I think I'm missing something. This is going to be disgusting. Is this big enough?
Y-
You
Yes,
can
sir.
see
Yes,
it
sir.
clearly? Okay, good. So we're going to just do a little revision of some of the things you did at CXC here. Trying to get these controls out of the way. Let's see. All right. Yeah. And this is a topic you've been exposed to, I think, as early as maybe force form, right? Where you talk about relations and what we call one-to-one relation and many-to-one relation and so, right? That's what we're going to talk about here. So, yeah, a little definition of what a relation is. It's a set of ordered pairs, and there's a reason why they call it a relation, because in each pair you can see that there's some kind of relationship between the force element. If I were to, where's my pen? If I were to come here, you can see that like there's some kind of relationship between this force element and the second one, this one and this one, this one and this one. There seems to be a relationship, and you can see it quickly, right? Can you see it? What's happening? What's happening there? What do I do to this force number to get the second number? What do I do to this to get this? Can you see
Plus
it
2.
already? Yeah, it seems so, right? Yeah. I will come to that just now. And we're saying that, okay, in well, we're getting some definitions clarified here, right? Um, the elements, the force elements of R, right? Of each pair then is what we call the domain of R, right? And the second element of each pair is what we call the range of the relation R, right? And well, this relationship here is one that we'll talk about extensively a little later. And the range is oftentimes a subset of the codomain. And there are times when it's equal to, right? So that's why I throw in that little equal sign at the bottom there. So the range can either be a codomain, sorry, a subset of the codomain, and at other times it can actually be equal to the codomain, right? I'll, I'll revisit this whole thought when we get into what we call functions, right? We're just at relations. I'm just introducing it back to you, right? Um, just a second, let me snip something and bring it over here. Why is this happening? Yeah. So there are ways of representing relations. Well, this is one way using set notation. And then we can represent it algebraically right? We can represent it algebraically. Yeah. There's these guys that ride around with that fudgical business. They make a lot of noise, man. They confuse me. Yeah. So here's an algebraic approach to represent the same relation here, right? And you're saying that x is such that x maps onto x plus 2, right? So it's like x is the input and x plus 2 is the output, right? Later on again, we're going to expand down here. Before we actually describe it algebraically, we're supposed to say what is the domain and what is the codomain, right? Normally, when you're in high school and so, you normally don't. I mean, I was guilty of that. When I teach relations, functions, and graphs, you don't describe the relation and later on functions. You don't describe them in terms of the domain and the range, what they should be, right? We're going to get to that just now. Good. So besides, okay, we can represent a relation using set notation. We can do it algebraically, and of course, we can use a little mapping diagram, right? A little mapping diagram that see if I can. Right? So you're all familiar with this. That same relation we had just now. I'm now using a mapping diagram, right? Or some people say it's an arrow diagram, right? Where, okay, the elements of the domain is here, the domain, and the elements of the, well, um, let's call this the codomain. What's this there? Right? Which houses the range, right? Which houses the range. We'll talk a little more about this just now. And then, of course, we can even represent the thing graphically, right? We can represent it graphically. Try to move this along. Right? We can represent the relation on a graph, right? In this case, it's a straight line, right? Think 0, this point here, down here 0, 2, down here is 1, 3, down here is, what's that, 2, 4, then 3, 5, and 4, 6, right? Yeah, there should be a 6 there. Yeah. So there are so many ways you can represent a relation. And this type of relation is what we call a one-to-one relation, right? It's a one-to-one relation. I think cutting and fetching these things over. I have a PowerPoint. Let me just share the PowerPoint because this whiteboard to adjust it takes some doing. So let me stop sharing for a moment. How do I get this PowerPoint over here? Oh, 1 second. Hmm. Give me a second. Advanced share. I think I have the share portion of the screen. Yeah. So you can see that, right?
Yes, sir.
Great. Good. So as I said, this relation we just dealt with is what we call a one-to-one relation. A one. I wonder why I'm not able to. Oh, when I click here, I was supposed to be able to annotate. Yeah, that's what I'm talking about. Yeah. It's a one-to-one mapping or relation, right? One-to-one mapping or relation. All right. Yeah. Look at another one. This out of the way. Okay. So here you have another um, type of relation. I think I have to erase this. And you can, well, I think I gave away the relationship, right? If you take the first element here, you square it, you get a second one, right? Same thing happens here. You square that, you get that. Square this, you get that. Square this, you get that. Square that, you get that, right? So the relation can be described as x is such that x maps onto x squared, right? Um, not very difficult. This, however, if you were to see it on the mapping diagram, you recognize it as a many-to-one relation or a many-to-one mapping, right? Because you're seeing like, okay, you see -2 and 2 goes to 4. You're seeing -1 and 1 goes to 1, right? Yeah, so there's a little different type. So we had one-to-one, now we're having a many-to-one, right? And if you were to represent that on a graph, that's what it looks like. That's what it looks like. We were to go to another type. This one is rather strange. It's kind of being given away here. X maps onto the square root of x, right? And the positive and negative square root. And in this case, you're seeing that let's take 1 for example. It's mapped to -1 as well as 1. So this is not a many-to-one. It's not a one-to-one. It's not a many-to-one, but it's a one-to-many, as you can see here. It's a one-to-many. See, like okay, number 1, it maps to 2 elements of the codomain. 9 goes to -3 and 3, right? And that's how you know one-to-many relation. I think there are a couple of computer science students in this class, and you will go even further. You will go when you study something called database management systems. I think there's a course like that, maybe in your second year or so. You're going to learn about many-to-many relations, which is much more complex, right? Much more complex than these here, right? And find themselves being useful in database management, when it comes to employee records and who is connected to who. It's not that simple, right? Maybe we're oversimplifying relationships here for your sakes, but it can get that far. And this is what it looks like, right? This is what a graph looks like. It's a one to many, right? What did I say? Many to one? No, this is a one to many, right? Relation. Good. So it comes. We're coming down to a special. Yes, Matura.
Sir, I have a question. How can you tell based on the graph if it's a many to one or a one to many?
You're trying to test me out or something? Somebody told you something in high school? Huh?
Pardon?
I said, are you trying to test me out?
No, I want to know, like, how would you know if it's a many to one or a one to many
What
based on
prompted the question?
So, like, for example, if you didn't give us the map and diagram before this, how can we tell based on this graph if it's a one to many or a many to one?
Write that down. Write the question down. And research it yourself. Anybody in the class knows that? I know from high school. Any in the class knows that? Hmm?
Sir, I think if you draw a straight line through the x-axis, if it passes through more than one point, then it means that it's not a function.
No, he's not asking that. He's asking about how do you know it's a one-to-one? How do you know it's a many-to-one? All right, we'll have to back up and let's see if we can answer that question. Good. So you're saying from the graph, you want to see that?
Yes, sir.
Good. So look at the graph, right? What the graph is saying for every element, every element of the codomain, let's go through here. Any element here, where it coincides the graph, it cuts one place only, right? Which means it corresponds to only one element from the domain, right? Every element from the codomain can be matched to only one element from the codomain. You see that?
Yes, sir.
And that's how you know it's a one-to-one.
So the codomain is the y-axis?
Yes, the codomain. This is the domain values are usually on the x-axis. And the codomain is here. Yeah. And remember, the range is a subset of this. We'll come to that in a moment. You had a different idea?
Oh, sir, I was genuinely puzzled, so that's why I asked. I didn't really know.
Oh, I thought you were told something in high school and you want to see. Let's see if this chap know.
No.
All right.
Yeah, no.
Okay. All right. Yeah. For the other one, let's go to this one here. Let me erase this here. So this is a many to one, right? So for each element of the codomain, let's take one, right? Let's take two. The number two, right? You're seeing that, okay, if you draw it, it meets the graph here, and you draw down, and that corresponds to some value here. Then if you were to project this line this way, meets the graph there, and you have another value of x here, right? You have another value, right? V1, and over here you have V2. So you have two values of x corresponding to or going towards one value in the codomain. So therefore, you're having a many to one mapping or relation. Right, you seeing that?
Yes, sir.
Good. When we come to function, that somebody was talking about drawing some line and all of that, right? So there is something called a horizontal line test, right? So if you have um, really it works for what we call functions. Not all relations it works for. That if you were to draw a horizontal line and it cuts twice, you have a many-to-one. Because the other one, remember you had this. You had a straight line. If you draw a horizontal line, it cuts once. And you say, oh no, this is a one-to-one. Right? But this one here, it cuts twice. So this is a many-to-one, right? So this one was one-to-one. This one was many-to-one. Where this falls down, let me erase all of this. Where this falls down is that third relation there. Give me a second. If I don't erase this, I think it will show up in the next slide. That's why I was trying to use the whiteboard and all of that. This one here, right? This one here. If we were to go here and we draw the horizontal line, we draw a horizontal line, right? So maybe you draw a line there. It cuts once. And you might want to say, oh, we got a one-to-one relation, but this is not a one-to-one relation. This is a one-to-many. So the horizontal line will fail here. But if you're dealing with, and that is why I'm saying your question was a little, sometimes you want to wait a little, right? So like functions, when you're dealing with functions, to figure out if a function is one-to-one or many-to-one, you will use that horizontal line test. But when you have a relation that is a one-to-many, this horizontal line test falls down, right? It falls down. What you're seeing here is that for one x value, you have two y value, right? So this is a one-to-many. And the horizontal line test will fail here, right? The horizontal line test will fail here. But analyzing the graph, right? Learning to analyze the graph is a very useful skill, right? Anyway, it's good that you ask a question. At least we get to back up and learn to analyze the graph and figure out whether it's a one-to-one, many-to-one, or a one-to-many, right? So that's the kind of analysis you'll have to do. The suggestion by a student, I heard one of the girls said, do the horizontal line test. If you're dealing with one-to-one and many-to-one, the horizontal line test will do. But it fails. It fails when we come to the one-to-many. Because it doesn't tell you anything useful now. Because if you were to draw the line, if you were to draw the horizontal line, it cuts once. And one might think, oh, this is a one-to-one. Right? Doesn't cut twice, cut once. And there's where, well, it fell through because this is not, well, what we'll call a function. Later on in the discussion, we're going to see that what functions are, right? And this is what we're talking about now. Right? So a function really is a special type of relation, right? And this is saying that, okay, a relation is a function if each element of the domain has one and only one element of the codomain, right? So when you were to look at the mapping diagram, every element here, an arrow has to leave it then. That's what they're saying. An arrow has to leave it. Not more than one arrows. If you have more than one arrow leaving an element here, that's not a function. And that would make the one-to-many relation not a function, not a function. So the one-to-one, as it's saying here, one-to-one and many-to-one relations are functions. It's sad that in just a few maybe months from now, when you're going to do, not you, I think some of the students already, when they're going to study analytic geometry, we're going to take this definition and throw it out the window. In that we're going to still call things like circles, and we can come to that in a moment. Circles, ellipses, and so we'll call them functions even though they're not by this definition, right? But we're gonna work with this for now. I don't want to just tell you about it and then throw it away right away. Right? So one-to-one relations and many-to-one relations are what we call functions, right? Are what we call functions. We'll come to that just now, right? And remember that girl was talking about a horizontal line test? Well, there's a vertical line test now that you can use to know if a function, if a relation is a function. Like, okay, we had a one-to-one, and they say you draw a vertical line, right? Draw a vertical line. If the line cuts, I should use a different color here. I should use a different color with this vertical line. If it cuts once, that's a one-to-one, right? It's a one-to-one function, right? No, I'm wrong. Once it cuts the graph once, you have a function, right? You have a function. So if you have this, and you draw a vertical line, it cuts once, right? It cuts once, so it's a function. That's a way you can figure out that a relation is a function. So even though this one is one-to-one and this one is many-to-one, they're both functions, right? And the reason why is that for every x value here, let's say x value, you got one value for y. You know, you got an x value here, there's a value for y, right? There's an x value here, there is a value for y, right? I'm supposed to draw it to reach there. Yeah, for every x value, there's one value for y, right? And that's what you call a function. Each element of the domain, it has a single match in the codomain, not more than one. The minute it has more than one, you're not going to classify it as a function, at least for now. At least for now. And everybody says you're getting more big. And as you get more big, you can bear more stuff, right? That is when we tell you the truth, the full truth, right? As of now, I think, well, I hope none of you believe that, well, there's something in Santa Claus, and so they tell the children also the garbage when it's small, and children grow big, they tell them, well, I've never seen so many movies made about Christmas like I'm seeing on this show, this streaming provider that I have. Oh God, yeah. Good. So I want to go a little into something that is, I would say, new, right? In that you weren't told this kind of thing at CXC, right? At that level, high school level. What happens when you're given a function? You know, you're given a function, right? So, oh, by the way, when a relation is a functional, we add this on. We say that, well, the function of x, this is how we write it. F, right? With a, what do you call this? A colon, right? X. I think most of the textbooks don't use this anymore, right? What they do, they call it, they say they do this. F, X. They put it in a bracket now. And we don't normally put the arrow. We say function of x is equals to x plus 2, right? So this was the old way, right? And, well, this is what we say now, right? This is what we say now. However, when describing a function, this is something that we're supposed to do. We're supposed to say what is the domain and what is the codomain, right? Normally, we don't do that. At high school, they just tell you a function. fx equal x plus 2, and in your mind, you think that, well, x is all the real numbers, right? X can take any value. And you think that, well, okay, maybe you don't even think of the codomain and range and all of that. You don't think anything about that, right? But what this bit of notation is telling you is that the function x, the function f maps R onto R, right? And that is telling you what the domain is, what the codomain is. Why this is very useful, right? Why this is very useful is that you have the power now to kind of define functions, restrict functions, extend functions. You can do a lot of things with this, right? So all right. Like in this case, because of the way this is defined, right? Because of the way it's defined, you see that in this case, the domain of the function is all the real numbers. The codomain is also all the real numbers. And in this case, you see that the range is equal to the codomain, right? And you're going to hear some terms if you do any amount of reading. If you do any amount of reading, you're going to hear of something called injective function. Injective. You're going to hear of surjective, right? You're going to hear of bijective, right? Bijective functions, right? What you're talking about here, well, usually, if you do any bit of reading, maybe you Google the thing and so, you'll see that they say injective function is what we call, they say it's a one-to-one, right? But when it's an injective function, right, it's not just one-to-one, right? Okay. The main condition is that it's a one-to-one, right? And sometimes you hear this term, it's an into function. Now, when you talk about into function, what you mean is that sometimes the codomain is not all mapped to. I'll give you examples in a moment. When you speak of a surjective function, right, they're not concerned whether it's a one-to-one or a many-to-one so much, but it's what we call an onto function, in that all the elements of the codomain are mapped to. And a bijective function is when it's one-to-one and onto. And I think I might have to go to, all right. Let me see this next. All right, let me use this one as an example. Let me clear out this part here, so you don't get too confused with all the information. So we're speaking about injective being one-to-one, surjective being, well, when the codomain and the range is the same thing. And bijective is both one-to-one and onto. Good. This function here, basically, if you were to throw it on a graph, right? It's a straight line. X plus 2 is probably looking like this. A line like that, where 2 is down there, right? Something like that. It's a straight line. Oh God, it looks like a curve, no? So it's a straight line. So this function is one-to-one. So it's into, right? Or what we call injective, one-to-one. However, you will also see that, well, remember this line extends in both directions forever, right? So the codomain, every element of the codomain is mapped to. Any number you take here, if you were to draw across, there is an x value to it, right? So the entire codomain is mapped to. Therefore, the function is onto, right? So it's both injective and it's onto or surjective. Therefore, it's bijective, right? So it's, as we said, it's one-to-one, it's injective. It's surjective because every element of the codomain is taken up. There's no real number, right, in the codomain here. No real number that doesn't have a matching x value then. There's no y value that doesn't have a matching x value, right? Okay, if you were to put it like this, y equal x plus 2. You give y any real value in the whole wide world, you can find an x value that will give you y. Isn't that so? Think about it. If I were to give y any real value, would this equation not have a real solution? Or x wouldn't have a real value? Yes. So in this case, this is a one-to-one. It's surjective, and therefore we can say it's also bijective. It's a one-to-one. All elements of the codomain is mapped to, and therefore if both of the conditions are satisfied, it's bijective. Maybe the other example is going to help you a little more. This is something new. I'm not gonna emphasize it so much. It's a bit of reading for you. I just want to widen out your horizons a little. Look at this one. So you have this function. Well, it's named g, right? And we're saying that g maps the real numbers to the real numbers, right? So here, I guess let me throw the graph up, and maybe this will give you an idea. The graph looks like this, right? The graph looks like this, right? I know it's not perfect. Good. So in this case, right away you see it's not a one-to-one. No, it's not. Right? You know that as a many-to-one. So it's not injective. It's not injective at all. Right? It's not one-to-one. Good. Now what about, is it surjective? No, it's not surjective either. It's not surjective because what? The codomain is this, all the real numbers. Let's take the number -1 on the y-axis. There is no x value that corresponds to -1. Therefore, there's a whole host of all the numbers less than 0, right, going down. In the codomain has nothing going to them, right? Has nothing going to them. So it's not even surjective. So it's not one-to-one, it's not surjective. And in this case, the range is just a subset. R, right, is a subset or is contained in the codomain, right? The codomain. What did we use? CD? The codomain. The range is just a subset of the codomain, right? This is what we call an into. It could be an into function, right? However, before we go to into, I want to just show you something. And here is where defining functions and saying what is the domain, what is the codomain, it gives you power then. What I could do now, I could say let G, right, be, let's go with R plus to R plus, meaning it maps the positive real numbers to the positive real numbers, right? Now, what this is telling me now that the graph doesn't look like the one we had before. The graph goes from, all right, 0 is excluded, right? So I'm going to put a hole here. Right? Let me make it more pronounced. Yeah, I want to erase the whole thing. All right, let me go here. So I'm putting a hole here, meaning 0 is not included. So the graph looks like this. The graph doesn't exist where R is negative for the domain nor the codomain. Right? So the codomain here is all the positive real numbers from here going up. And the domain is all the positive numbers. So what you have effectively done there is that a function that is normally, you will think that this is a many-to-one function, right? And it's not surjective either. But now you have a situation where it is one-to-one, so it is injective, right? It's injective. All the elements of the domain are taken up, right? Because remember, the domain doesn't exist here. Sorry, the codomain doesn't exist here. The codomain are the y values from any number greater than 0. So every one of these y values, every one has a corresponding x value, right? Every value on the y-axis now, the positive y-axis, has a corresponding x value. And therefore, you have a situation what we call surjective function, in that the range equal to the codomain. It's equal to the codomain, right? All the elements of the codomain are mapped to. So your range is equal to your codomain, right? Oh, neglect this, what I'm saying here, right? This was different. So you have the power to modify what your input is and what your possible outputs are, right? And you can make a function one-to-one. You can make a function surjective. You can do that. I probably wanted to show you let me see if I can stop sharing. Just to give you a second example. Let me stop sharing for a moment. I want to go and use a whiteboard for a second. Oh, no. Is there a whiteboard here? Y'all can see this whiteboard, right?
Yes, sir.
Good. So let's take the function okay, let's go up like that, right? And function y equal e to the x. Now you can define this function y equal e to the x. This function, it goes down here, approaches 0 but never really reaches it, right? This is a function, it's one-to-one, right? Now it depends on how you define this function. If I define this function, right, that okay, f maps r plus to r plus, right? Now in this case, this function is both a one-to-one as well as it's surjective, right? So it's also bijective because it's one-to-one. Every y value that I get one x value. Every y value, I get one x value, right? Every y value, I get one x value. So it's a one-to-one. It's surjective based on how I defined it here. R plus to R plus, because the codomain is the positive real numbers, right? So all the positive real numbers has something going to it. So it's surjective, meaning everything is taken up. However, if I were to change something now, I could make this now. I could take this out and say, let f maps R plus to R, right? Well, oh, just now, you know something? When I said R plus here, I still use negative values for x. I think I shouldn't have said that. All right, let me take that out. You can leave that in, right? Let me take it out. R, right? R. When you say if the function maps R to R, you are making the codomain. What is that thing here? Yeah. You're making the codomain all the real numbers, but guess what? There's no value here, right? The graph doesn't exist under here. So there's no X value to map to anything under here, right? So what is happening? The graph doesn't exist here. But your codomain includes -1, -2, -3, and so on, right? All the negative values. So while the function is still 1-to-1, it is not surjective anymore, right? It is not surjective. See? So it fails to pass the surjective test there. So while it's 1-to-1, it's not surjective. So you can make the function, yes, Hemraj.
Sir, how is the function still 1-to-1 if there's nothing to map to at the bottom?
Well, remember the definition of 1-to-1. Let me probably erase and draw it back properly, right? Yeah, let me draw it back. So the function comes like this, right? So for every y value, there is one x value. There is no y value under here. The function doesn't exist here. For this y value, okay, let's say down here, you go here, you come down here. And that's what 1-to-1 is about. For every value here, there is one value here. That's what 1-to-1 means. For every value here, there is one value here. That's the definition of 1-to-1. So down here, okay, -1, -10, whatever. The function doesn't exist there. So you don't have to worry about it. They're not in your range, right? They're in your codomain, depending on if you define it that way. Right? But nothing maps to them. Nothing maps to them. Right? That answers your question?
Yes, sir. So
Study it some more. It's deep. It's deep stuff. I just want to take you all there just to what do I do to stop?
sir, but if you have a case like this again, just ignore it. But it's not gonna be surjective anymore.
I don't get that.
If we have another graph like this, right, where we have the two numbers at the bottom, but there's no, it's gonna be 1-to-1 still, but it won't be surjective anymore.
Yeah, because there's no, as I said, there's no value of x mapping to any negative number down here. Because the graph doesn't exist here. How you do the mapping? You take a y value, you draw it to reach the graph, and then you see the corresponding x value. But down here, let's say, all right, let's say -2. I'm drawing, I'm not reaching no graph because there is no graph. If there is no graph to meet, then there's no x value to correspond to. You see?
Yes, sir.
So these numbers can be in your codomain, but they're not in your range. Right? They're not in your range. They're not outputs. They're not possible outputs of your function. Another tricky one, let me give you another tricky one that is very interesting. I'm giving away all the answers from your worksheet here. Look at this one. Yeah.
Sir, so if it's not surjective, it can never be bijective?
No, but remember, for it to be bijective, it has to be both injective and surjective. Right?
Okay, sir.
Think about it, yeah, set theory. So we go like this, a function like that, right? Now a function like this is a 1-to-1 function. So when you define, let's say you go with f maps, let's go with r, well, in this case, if you don't say r to, let's say r, right? This is not a function because the negative numbers here, -1, -2, -3, they don't go to nothing. So in other words, when you draw the mapping diagram, -1 doesn't go to nothing. -2 doesn't go to nothing. and therefore it's not a function. So this function, even though they don't tell you this in high school, you have to define it that when you speak of, well, this is the logarithmic function, right? Log x. That's what it looks like. You have to say that r is positive. You have to say that. We don't usually say it. We just give the students the function and that's it. We say, all right, y equal log x. But we don't tell them, you know what? The domain has to be positive. Because you can check it. Log of 0, what happens? Error. Log of -1, error. Log of -10, error. Because the negative numbers are not in the domain. And therefore, you have to spell out and say, this function maps r to r. Notice you can't put negative. You can put negative and positive here. But r covers all the numbers now, right? So any value you go here, there is some value, you go across. There's an x value. It's a one-to-one function. You come down here, like you said just now, go across here, and you go up here. It's a one-to-one. As well as, this is a surjective function as well. It's a surjective function because all the values, all the y values got an x value corresponding to it. All. Right? So you have a one-to-one situation, you have one-to-one, and you have a situation where the range equal to the codomain. So it is both an injective function as well as a surjective function. You're seeing any sense in all of this? Right? So I didn't want to stick with what you did at CXC. You want to open up your mind a little more, right? Want to open up your mind a little more. They're all in your worksheet. They're all in your worksheet. What you don't do at the high school level, they don't tell you, you know what? Before you run and define a function, you got to spell out what's the domain, what's the codomain, right? You have to spell that out, and then is when you can, say whether the function is one-to-one, whether it's, the range is equal to the codomain or it's just a subset of that sort of thing, right? All right, so let's go back to, what's happening here? Let me go back to, this thing here, right? Well, this is another example, just to highlight. This is the function. I never liked let me not elaborate on this. The reason why is that this R, the 0 is not, there's a way of saying that 0 is not in the domain here, right? You say the function R the function f maps R onto R, right? And the function is 1 over x for all x is not 0. This is a way of saying that 0 is not in the domain, even though you kind of get the impression there. I'm not a fan of this here. I like this one. I like this one where it kind of tell you here that 0 is not in your domain, right? And probably you all know this function here, what it looks like, right? This is the curve 1 over x, right? It goes like that somewhere, right? So x can't be 0. 1 over 0 is undefined, right? Yeah. So your domain is what they say here. All the real numbers except 0. This is another way of writing it. All x is not equal to 0. Your codomain is all the values of y, right? Your range is all y is not 0. So what you're seeing there is a small difference between the range and the codomain. The only thing that is missing from the range that is in the codomain is 0. And that makes it not surjective. The range is not equal to the codomain. For there's a girl who was always questioning, who was it that was talking? The girl that was asking the question. So in this case, are you listening? The range is not equal to the codomain. It's just shy of one number, 0. So while 0 is in the codomain, it's not in the range, right? Because there's no number you can put whatever under there. It can't be 0. It can't be 0. So 0 is not in the range of 1 over x, or the function 1 over x, right? And you can also see that this thing is 1-to-1, right? It's 1-to-1. It's a 1-to-1 function. It's just that it's shy of one value. Y can't be 0 to make it surjective, right? It's funny. All right, good. So enough of that. Enough of that. I think we spent enough time on that. So let's talk about. Oh, I need to erase all of this. And 1 second, let me put on my fan because this room is getting hot. These concrete walls or something else. 1 second. Whole country doing something that is crazy. Building with concrete all over. Yeah. So here we're talking about combining functions. We don't spend no kind of time here. It's got to do with, you can add 2 functions, you can multiply 2 functions, you can even divide 2 functions and so, right? That's what this is all saying, right? You can add 2 functions, you can subtract 2 functions, you can multiply 2 functions, you can divide 2 functions, right? They call it function algebra, or they call it, what is it? Arithmetical functions, right? As an example, look here. So you have what here? You have 2 functions. This is fx, that's gx, and you can add them. You simply add them algebraically, right? You can subtract them. I'm using this asterisk here to indicate multiplication because I don't want you to confuse multiplying 2 functions with the composite of 2 functions, which we're going to next, right? So we can add them, we can subtract them, we can multiply them, we can even divide them, right? And by the way, you know, I guess by now you should be able to do this division here. This can be simplified further, right? Now that you did factor and remainder theorem and you do long division, right? So you can be able to divide this some more, right? Good. So this is basic, right? This is basic. I want to focusing on this does not mean multiplying 2 functions is not the same as the composite of 2 functions, which I'm going to next, right? We talk about function composition. And sometimes you see this symbol, right? It's not multiplied. You are forming a composite, right? In other words, you are creating a function that can do the job of 2 other functions. So like long ago, you had a telephone used to do one thing. A camera used to do one thing. Nowadays, you have one instrument that is doing everything. And you know what I'm talking about, right? These days, nobody, you know, you don't have a camera. Most people don't have a camera, right? And the thing we call phone, we hardly use it as a phone, right? It's a composite of so many functions, right? And that's what we're talking about here. A function that can do the job of 2 others, right? But in a certain order, what I mean here, let me just illustrate with an example. So you have 2 functions. This is fx. This is gx, right? This here is what we refer to as a product of the two, right? You multiply this by this. I know some of the textbooks are going to indicate that fg means the composite of f and g. But at least in this course, when we say the composite of f and g, we mean we write it like this: f with a little circle here, g. And the composite of g and f, we write it like that, right? So for the sake of this course, because we talk about function multiplication, right? So the multiplication, we did it before, that's what we get. If you multiply this function by this function, we get that. That's no problem there. You can try it on your own in your own sweet time, right? But when we talk about the composite of f and g, what this is telling you is that g is performed force on the input x, and the output of g goes into f. And that's what's happening here. Right? So you take the input x, you put it in g, you get 2x minus 1. You take that output now and you put it in f, right? So remember gx is 2x minus 1. So you put that in f, right? So everywhere you see x in f, you put 2x minus 1. That's what's happening here. Simplify, you get this. On the other hand, if you have gf, right, the composite of g and f, notice the function inside now, on the inside is f. In other words, you're putting this entire function, 2 plus 3x minus x, in the place of x in g. That's what's happening here. So where x is in g, you put the whole f. Simplify, you get this. Please note that the composite of f and g and the composite of g and f are not the same, right? It's not the same. What do you say? It's not commutative, right? So unlike, 2 by 3 and 3 by 2 is 6, yeah, but not with function. Function composition is not commutative, right? The order is important. Any questions there?
No, sir, no questions.
Great. And you did this in high school, right? This is just a rehash of high school. Because I see some of you coming with 14 grade 1 and 15 grade 1 and so. I hope maths is inside, and you have to do this. Unless you go through high school, beat the test, and don't know half the stuff. It can happen. You just learn to crack the people, and that's what is being taught in most of the lessons, to beat the people. So maybe you're not really a good thinker. You haven't developed your thinking skills and so, but you can get a grade 1, right? Your grade 1 doesn't say anything about your ability to think and all of that. Yeah. Good. So to illustrate function composition, look here. So these were our two functions, g and f, right? So if you were to do, okay, g of x takes an input x, right? And gives an output of 2x minus 1. fx, right, takes an input and does this to it. 2 plus 3x minus x squared. Good. So if we were to take, let's say, the number 0, 1, and we were to put it in g, we will get the output minus 1, 1, right? If we take that output from g and put it in f, and we do these operations here, we get these outputs, right? So here we have two functions. We have an input at the beginning, 0, 1, and we pass it through two functions. We pass it through g, and then the result that comes out of g, we put into f, and we get minus 2, 4. The composite of the two now, remember we found the composite in a previous slide? If we were to take 0 and 1, it will take us straight to this output minus 2, 4. In other words, the composite of f and g does what g followed by f would have done. right? So the composite does the what two or more functions would have done individually, right? If you were to take the output from one, put it in another, take the output from the second, put it in the third, you can have a composite function that can do all those things at one go, right? Which is what a device in your hand today is doing, eh? Everything in one. Good. Y'all got the idea what function composition is all about? It's different. Keep in mind, it's not function multiplication. That is a whole different thing, right? That is a whole different thing. Function multiplication does not perform the function of more than one other functions, right? Keep that in mind. Function composition is what does it. Good. We're going to another something familiar, what we call inverse functions. Inverse functions. And basically, a function and its inverse, basically what it does, the inverse reverses the operation of the original function. And we have two examples here, right? If you take fx, and fx is 3x minus 2, and gx, which is x over 3 plus 2/3, right? Well, of course, you might know, but these two are the inverse of one another. Gx is the inverse of fx, and fx is the inverse of gx, right? If you were to take x and put it in the composition of these two, you will get x, right? If you take this whole function here and you put it in there, you will get x. If you take this whole function here and you put it in here in the place of x here, you will get x. So whenever that happens, right, where the composite of two functions is equals to x, one is the inverse of the other. Because what that is saying is this, okay. All right. The diagram in the next slide will illustrate it, right? The diagram in the next slide is going to illustrate. These are with some numbers. You put in -1, you get out 5. You put -5 in gx, which is the inverse of fx, it will take you back to -1. Similarly, you take 2, you put it in gx, you get 4/3. If you put 4/3 in fx, you get back 2. These two functions seem to be reversing one another, right? So it seems, at least intuitively, right? Look at the diagram here. So if you take these numbers, okay, -1, 4/3, put it in fx, you get this, right? You get these. If you were to take these and put it in gx, it gives you back these, right? So fx and gx seem to be reversing one another's operations, right? One is reversing what the other is doing. Therefore, two functions that are, doing the opposite of what the other one was doing, right, are inverses, right? That's just a technical way of writing it just now. This is an even more technical way here, right? Well, I think this is what we had earlier. If f of g, right, the composite of f and g is x, and the composite of g and f is x, well, then f and g are inverses of one another. As a matter of fact, though, it's one of the times when a function composition where the order results in the same thing, right? Usually it doesn't, right? I mentioned before that f of g and g of f usually are not the same thing. In this case, they are the same thing. So if two functions are inverses of one another, then the composite of f and g and the composite of g and f are the same. It's an exception to the rule, right? And that's what all of this is saying here, right? And if this is the case, if the composite of g of f is x and the composite of f and g is x, well then it looked like these two functions are just reversing, you know, what the other one did, right? So they're inverses of one another. That's what all this write-up is about. The process of doing it, there's an arithmetic process that, you know, we've been doing. I think you know this from high school, you know, where you put y equal fx and you swap around x and y, you make back y the subject, and whatever is the result is the inverse, right? I don't have to go through it, right? You can always take this video and watch it back. I think I made available some notes with this process inside, right? But I'm just gonna show you an example, which I think you know very well, right? So you have a function, 3x minus 2 is the same f and g that we were dealing with, yeah. And you want to find the inverse of f. So they say first you put y equal fx, then you switch around x and y. It's an arithmetic, you know, process like that that always works, right? I would say, what should I call it? It's not so much arithmetic, it's more algebraic process that works, right? They have found it to work. And then you make back y the subject, and here it is, y equal this, which we will now call the inverse of x. Right? So the process is very simple. I think this is high school stuff. A question that might baffle you, and I took this from your high school textbook as well, is this one. Are we, the class is still with me, or y'all are tired mentally and got lost? Wonder what time it is. Look at this one. I remember seeing this in the high school textbook. Oh, 4:30, we got some time. So, okay. You're given hx equal x plus 4 over 2x minus 5. They ask you to find the inverse. Okay. You go through the process and you find the inverse here, right? But then next they tell you to solve x plus 4 over 2x minus 5 equals 7. And I know you know enough algebra to solve that using the other methods. But I think what they mean here, is there a way? There was something missing here. I wonder if I had to. See? Nope. All right, something is missing here. And that's the part where it says here, you have to solve this part, right? So I'm not going to do the inverse, right? This is the whole process. So we got the inverse. So what this statement is saying, right? What this statement is saying, that you take an input x, and when you put it in the function, it gives you y. Therefore, if you were to put 7 in the inverse function, it's going to lead you back to x. In other words, it's like you take x in the domain and it gives you 7. So hx is doing this. hx is doing this. What h inverse x is doing, it's doing this. Oh, 4 plus 5x now. The inverse is going to take 7 and give you x. The inverse is going to do that. So all you got to do now to find x, or to solve, out of space. Oh gosh. Where do I put it? To solve, I'm not going to write out the equation, right? X equal h, h inverse 7. So you just substitute 7 in here, right? And that will lead you back to x. Right? So if you understand what the inverse does, that's why they ask you to solve that equation. You notice they use the word hence. They mean you have to use this inverse. I think somebody's Mariah Cummins. I think you need to mute yourself. Yeah. Yeah. So that's why they ask you to find the inverse and hence solve this equation. Because the inverse is going to take 7 and churn out the value of x. If we understand how the function and the inverse works, right? If I'm to go that back over, what's the thing? The thing show up here eventually, watch. What kind of miracle happening here? The thing showed up here, watch. So x is equals to h inverse 7. As I said, the original function, right? The original function here takes x, whatever it is, and churns out 7. The inverse, on the other hand, what it can do, it can take 7 and churn out the value of x. And that's what we're doing here, right? So we got the inverse. What we're going to do, we're going to put in the place of x 7. And that will lead us back to the x that is here, this x and this x, which happens to be 3. And you can check it, right? That it's 7. Is that a difficult concept? If it puzzles you, I can tell you when I was a kid, right? I didn't have that Raymond Tulsi book that you all use. We had an old book, if I remember well. There are 2 books available in our day. Certificate Maths by Greer and Lane, and there was Oxford Mathematics. Can't remember the writer of that one. But when I saw this question, this type of question, I was always puzzled. And for some reason, I didn't grasp it at the time, nor did the teacher attempt to explain it, right? It was later when I became a teacher, I said, look, I got to be able to understand what's happening here, right? So that students can get some insights, right? What isn't mentioned here, about inverses is that for inverses to exist, I must mention this. For inverses to exist, you must have what we call a surjective function. Let me see if that's right. No, because you can have 1-to-1 would have inverses. Many-to-1 doesn't have inverses, right? So when you do okay, a function has to be, I'm wrong about this one. It has to be bijective before you can have an inverse, right? You must have, let me illustrate. I think I have to go back to my, it has to be bijective. I'll tell you why. I need to stop sharing here. Probably. Yeah, good. Why are all these things turning up on the screen, man? A whole set of controls. What is name? These people zooms in to clear up this board. You're giving me a board and you put in icons all over its place, toolbars and what. Come again. Don't show this again. Why are you showing me over and over? I need to ask people what's going on, and the people tell them they're putting too much stuff on the screen. Yeah, good. So remember, oh, you know what? I missed something. I need to show you another slide before I come here. Sorry. Sheesh. Yeah, let me show you this other slide. So this is the slide, right? Talking about the graph and their inverses. So I mean, there are people who studied, they looked at graphs and their inverses, right? And functions and their inverses and their graphs, the relationship between the graphs. And what they found is that a function and its inverse, they're mirror images of one another in the line y equal x. Now, this is very important because this can actually tell you now that certain functions will not have inverses, right? It will not have inverses. And let me probably, once you have a good look at it, I'll stop sharing and go back to that whiteboard. They're going to get a whole set of writing on this thing. Good. So if you were to have, okay, you have a function and it's some kind of straight line. You know, it's some kind of straight line. Now this, it's a one-to-one. It's surjective. Therefore, it's bijective, right? So if you were to find the inverse of this, maybe it's going to be over here, right? So the line y equal x is here. So its inverse is also one-to-one. It's surjective and it's bijective, right? But let's take a function like this now. Let's say, okay, this one here. Let's take a function like this. And let's call that y equal x squared. So this is not one-to-one, right? It's not one-to-one. If you were to, let's say this is the line y equal x, and we were to find the inverse of this, right? The graph will look like this. This part is going to be reflected this way, and this part is going to be reflected this way, right? So this here is not a function. Not a function, right? It's not a function. You see that? So this here was a many-to-one mapping, right? Or a many-to-one function. The inverse, while you can calculate it, I remember, and I'll tell you a fun story quickly. Let me see how much time I have. Can't do any kind of storytelling with this class. Yeah, time is too short. Yeah. I remember for the teachers who were in the class, I remember many years ago, I was doing, I think, my DPED, or, yeah, I think it was at my DPED. You have to do practicum. And one of them was to, I had to do what we call, I had to critique another teacher. So we videoed a teacher teaching a class, and she was actually finding the inverse of a quadratic. And we noticed that the video was chopped off at the end. Nobody, including the lecturer, doesn't understand why the video is missing the end. So in my report, I wrote that the reason why the video was chopped off at the end is that the teacher realized that the inverse she found, and one thing, the mathematics does give you a calculation, right? Watch. If you get y equal x squared, right? You swap around. So you get x equal y squared. Then y equal to the square root of x plus or minus. The mathematics does give you an inverse by calculation. Yeah, there is an inverse. But guess what? That inverse is not a function. It's not a function, right? Because this is what you get. Because here you have an x value that maps to two y values. So you have a one-to-many, right? You have a one-to-many, which is not a function. You see? Oh my, what happened there? Somebody erased what I had on the board? Oh gosh. Oh my, somebody did something there. Yeah. So let me go back to the function. If I were to take that same function now, that y squared function, and I restrict it to just here. So this is y equal x squared, right? Y equal x squared. And I defined it as f maps R plus to R, let's say R plus. No, let me not say R plus. Let me say R. Right? So what we have here is a one-to-one. Right? We have a one-to-one. And if we were to reflect this, we will get this. Right? We'll get that. So down here, this is line y equal x. Right? And we're taking out the number 0 from the whole thing, right? So we're using, all right, y. Let me put R plus here just to be sure. Something is happening there. I don't know why this cross is come up. Yeah. So the original function, this is y equal x squared, and this is y equal to the square root of x. And by that, we mean the positive square root, right? Because notice our function maps R to R plus. See that? Right? Well, who is doing that now? Erase what you did there. And I think when you erase everything. No. Yeah, who did this, man? I think you got to erase this thing here. Yeah. Yeah. So in this case, the function does have an inverse because the way we defined it, f maps R plus to R plus, it is a one-to-one, right? It's one-to-one, right? And it's also surjective. Right? And that will now allow us to find the inverse. So keep this little thing in mind. If all this injective, surjective thing is confusing, generally a one-to-one function would have an inverse, right? But a many-to-one would not, right? It would not. The calculation is going to give you something, right? When you do the calculation, yes. But whatever you obtain is not a function, right? So you have to ensure that the function is defined in a way that makes it one-to-one. If not, you're going to have an inverse that is not a function. Good. I think we're a little short on time. I wanted to touch on something on graphs quickly. I'll probably have to clip that. Let me see if I can quickly graphs. Where's graphs? I'll just speed up that one. And I'll leave out some things on graphs that yeah, right? I'll just speed up this whole graph thing just to finish before our time expires. Huh? Good. So how do you draw a straight line? You know, you have a straight line, y equal to x minus 1. Well, you simply you can choose a number for zero for x. In this case, we choose 0, right? Yeah. We choose 0, put it in there, you get minus 1. So you get a point, 0 minus 1. That's 1 point. And then you can choose another random number. It's 3. I wonder which student is writing on the slides as I go. What really wrong with some people, right? Yeah. So you choose another number, and it can be any number. I chose 3, right? Some people also do this. They'll put y equals 0 and then find the corresponding x value up here. That's okay too, right? But you can choose another x value, put it in this equation. You have a corresponding y value. So you have 2 points now, 3, 5. That's all you need for a straight line. You need 2 points plot them, right? Plot them there and there, and you draw a line straight through. And that's your straight line, right? It's a quick way of drawing a straight line. You know this before, right? From high school? For a quadratic graph, if we're able to factorize it, as in this case, you get some idea of where it will cut the x-axis, like this here. This is going to tell you at -1, notice I use the opposite sign, and -5 are the two, what we sometimes call, oh my, you know, if I figure out who that student is, they are going to have an F in this course. The next time I see that blue name comes up there, you are going to have an F, right? Yeah. So we got the critical points, -1, yeah, -5. And then we can also get something from this 10, right? That's the y-intercept. And well, we have sufficient. And then we know the coefficient here is positive, so the graph is going to be like a U, right? You remember all of that from high school? And you're able to sketch your graph, right? Good. If you were able to complete the square, well, you can even get some more information, right? So, all right. You take this, you solve it, you get, you put it equals 0 and solve. That's how you'll get that and that. But you also, okay, we got a 10 from up here. We got a -3 here is where the minimum point, the x value, x equal -3. That's what you call the axis of symmetry, remember that? And the minimum value is -8. That's this here, right? So you get some more information when you're able to complete the square. So your graph has a little more detail, right? Good. One second, let me just. Just to introduce something a little new to you. We're going to deal with this, I think, next week. I'm watching. I'm running a little tight with dates for test 2 and so. All right, let me go here. So this is a new function I'm introducing to you here. And it's the first function I think you're going to see that involve what you call the function being defined piecewise. Right? Usually you are used to a function is defined by one equation. But here you're seeing a function defined by two different expressions. Fx is equals to x if x is more than 1. And fx is equals to minus x if x is negative. Right? That's one way. If you want to define it with just one expression, this is how you do it. Right? That fx is equals to the positive square root of x squared. This is kind of cumbersome. And that's why some choose to define it this way. It means that when x is negative, okay, -1, y is +1. You just change the value to a positive. When x is -2, y is +2, and so on. When x is positive, you don't have to do anything. Y is the same value. When x is 3, y is 3. No, you don't have to do anything there, right? As they say here. Fx is equals to x when x is greater than 0. But when x is negative, take the opposite sign. Take the negative up. So -1, -1 is +1, right? And so on. Very important function in mathematics. And if you were to study any kind of advanced mathematics, you'll see how useful this particular function is, right? Good. I'll come back to this when we deal with something called absolute value equations and inequalities and so. We'll come back to this function. the definition and all of this, right? Yeah, it's basically when you speak of the absolute value of a number, it's the length of the line segment from 0 to that number, right? So like -3, right? The length of the line segment from 0 to -3 is 3, right? The value -3 is less than 0 and 1 and so, but the length of the line segment, the modulus, the size of that line segment is 3, right? That's why the graph is of this nature. There's no negative size, right? When you're dealing with the length of a line segment, you can't have a negative. It has to be positive, right? But somebody's still writing on this screen, you know, why you play? I just want your name, or girl. I just want your name, and you're all right. Yeah, where am I? So let me touch on a little bit of transformation of graphs, right? Here you have a function fx equal x squared. That's this red here, right? The red you see there. Let me erase all this, yeah. So if I were to just add 3 to the function, right? Add 3 to the function, you have x squared plus 3. What happens is the function goes up to, and this purple, I hope this is purple, yeah. That's the graph up there. If you were to subtract 3 from the function becomes x squared minus 3, this green graph at the bottom here. So when you add a number, it goes up. When you take away a number, it comes down, right? And notice that's, you add a number or subtract a number to the output, right? Notice you're adding C or subtracting C from fx, the output, right? So you end up with a vertical shift, either up or down. You can have what you call horizontal shifts now. Like if you have a function, fx equal x cubed, that's this red function here, right? The red graph. If I were to add 2 there in the input, you will end up with x plus 2 cubed, right? Well, you can expand that out if you want to, right? And the function becomes, now when you add 2, what happens? The function goes to the negative side. That is purple here. That is purple, right? Don't be tricked. It's not the green. The green is when you subtract 2 here. When you subtract 2, right? You're going to get x minus 2 cubed. That's this function here, right? It's going to be this function here. And you can use, there's that function I tell you about a lot. What's it? Desmos. Desmos, you can type this in and experiment more with the function, right? So here you have a horizontal shift now, right? But notice when you add 2 to the input, the graph shifts to the negative side. When you subtract 2, the graph shifts to the positive side, right? Keep that in mind. Okay. Okay, so this one here, it involves both a horizontal shift as well as a vertical rise, right? So here we got the base function is x squared, that's the red there, right? But if I were to adjust the input by -2 and then add 4 to the output of that, look at what happens. The red, it shifts 2 places positive and then go up 4, right? See that? So I actually combine 2 movements there, right? So take note of that. You could actually, if you see a function like this, you can know, well, all right, the graph is, or you can write down the equation, right? Or the expression for the function by just watching it. I mean, there are other ways, but that's one way. You know the base function. You know, man, this thing got to be related to x squared somehow, right? But you can actually come up with it in this form. And then you can remove the bracket and simplify and all of that, right? I'm just opening up your appetite here for this kind of thing. This is a big study by itself, right? And then there's reflection in the x-axis, reflection in the y-axis, right? So to reflect a graph in the x-axis, you just negate it. Whatever is the output, just put a minus to it. That would flip it over to the negative side, right, of the y-axis. Sorry, the x-axis now. When you put a minus here, the function is reflected about the x-axis. That's on the negative side of the y-axis. You see with a graph just. And when you reflect in the y-axis, the input is what you change to negative, right? And just to show you what I mean, right? So you got a base function x squared. Putting a minus sign in front there, you end up with this purple at the bottom here, right? So it's reflected in the x-axis. So the graph goes over to the negative side of the y-axis, right? And then this one, the base function is 2 to the x, which is the red. And if I were to put minus x in the place of x there, it's reflected in the y-axis. It's gone over to the negative side of the x-axis here, right? But going up there, right? So it's a good example of a function that is reflected in the x-axis and the y-axis. All of this is related to something called, and you can write this down and research, odd functions and even functions. Find out what they are. It's related to what I'm talking about. Odd functions and even functions, right? There's too much packed in the course, you know? And then this is a famous function. It's among the simplest of rational functions. Rational function got to do with a function that something over something, right? I'm not going to get into graphing them. I do have some notes here. You have to be fresh before you can deal with this. I'm not going to get into it. We are going to deal with rational inequalities. But maybe if I have some time the next time, I will deal with it, right? But this is a base function, 1 over x, that you must be familiar with. It's going to come up a lot later on, right? So we're going to stop there. I think we overdid it this afternoon. Now it's 5 o'clock already. Yeah. Right. So all right, we'll stop there. Stop recording. Yeah.